Hi, this is Dr. Lusher, and this is a video on using measurements and calculations. This builds on the previous video about significant figures. So in chemistry, we often calculate with measurements, and that kind of implies a few things. We have to keep track of units, and we also have to keep track of uncertainty. So here's a couple pretty common calculations that we do. We do velocity sometimes, densities pretty often, concentrations pretty often, maybe volumes of different shapes. And so any of these calculations, these measurements that go into them, like distance, mass, volume, etc., they all have a certain level of certainty and a certain number of significant figures. So when we multiply or divide two measurements, or any number of measurements actually, the measurement that has the least number of significant figures, that measurement drives how many significant figures are on the answer. And good thing to remember is a chain is no stronger than its weakest link. So an example, if we're taking the density of an object, this object has a mass of 67.22 grams and a volume of 11 mils, 11.0 mils. So this mass has 4 significant figures and the volume has 3. So how many significant figures should be on that density? 3. Second example, if we're doing an area, 1,400 meters by 107 meters, that 1,400 meters as written only has 2 significant figures. So the area should only have 2 significant figures. The rules for adding and subtracting are a little bit different. The process is to first line up the numbers that you're adding and subtracting. Line them up by their decimal places. Then you add or subtract like you normally would. And the rightmost decimal place that has significant figures in it for everything being added or subtracted, that's where you should have digits in your answer. If there's no overlap of digits, then the smaller value actually doesn't affect the larger value. So let's look at some examples of this one. So let's say it's 15.4 miles from my parking spot on campus to a restaurant. And I measure that using my car's mileage. And I know that using a pretty accurate pedometer that my office to my parking spot is 0.12 miles. So what's the total distance? So the math part is easy, but here's what I mean by lining up the decimal points, the decimal places. I can see when I write my addition vertically like this that the tenths place has numbers for both of these measurements. And so the numerical answer is 15.52 miles, but since the hundredths place is unknown in the first distance, that mileage could really be anywhere from 15.35 to 15.449. And that sum, therefore, could range over a pretty good amount of mileage there. So we don't want to say 15.52 because that implies that we really know that 2 pretty accurately, when in reality it could be varying from 15.47 to 15.56. So we round to 15.5. Sometimes the values are so far different that you can kind of take a shortcut. For example, I might have learned 16 years ago that the Earth is 4.5 billion years old. And does that mean that the Earth is 4,500,000,000 and 16 years old? Well, sure, it's older than it was 16 years ago, but we don't want to say that the Earth is 4,500,000,000 and 16 years old because that implies that we really know the age of the Earth to the year. Same thing if you have a swimming pool that holds 2,500 gallons of water and you throw in a cup. Yes, there's more water in there now, but you can tell that the added amount isn't really affecting the volume so significantly that you should report it as 2,500.0625 gallons. What about unit conversions? I've put up a video about unit conversions. I put that up last week. Do I need to consider significant figures? And the answer is yes. But oftentimes a conversion of units doesn't actually change the number of significant figures because so many of our conversions, especially moving between metric units, those are exact equalities. For example, there's exactly 1,000 meters in 1 kilometer. But there are conversion factors where there's measurements or rounded values. Some examples, any sort of metric or metric to imperial equivalency, like 1 inch equals 2.54 centimeters, that's a rounded value, that's not exact. Also, a lot of our things that we look up in chemistry, like molar masses, Avogadro's number, we'll get to calculations with these in this course, but most of those are measurements. So Avogadro's number, 6.022 times 10 to the 23rd, only has 4 significant figures. Good rule of thumb is that if you are looking up a reference value, some kind of chemistry number, you want to make sure you find a reference value with more significant figures than your measurement. One periodic table might report molar masses to 3 places, one might report to 7. So if you're at a degree of accuracy where you have that many decimal places, you want to use the periodic table that reports that gives you more decimal places. So just a couple of philosophy things here. Think about how measurements might have been taken. With the swimming pool example that I gave, if it's written at 2,500 gallons, that it wasn't measured with tablespoons or like measuring cups. It was measured with something really rough. And so how you calculate with that measurement is impacted by the roughness of that measurement. Let's do a little bit of practice. I've given you a video on counting up the number of significant figures, so hopefully that's feeling a bit comfortable now. Let's see what happens when we calculate with these significant figures. So concentration of a solution that is 42.0 grams of solute and 2.67 liters of solution. This is a division. We haven't talked about concentration yet, but looking back to one of those early slides, it's the mass divided by the mass of the solute divided by the volume of solution. And we get, when we type that in on our calculator, we get 157.303, some more decimal places after that. What do we round to? Well, both of the mass and the volume have 3 significant figures, so we would want to round to 3 significant figures. And that would give us 157 grams per liter. Let's try a volume. Say we have a cube that's 0.0267 meters on each side. The volume of that cube is the length cubed. And again, on our calculator, it just gives us a whole mass of numbers, 0.0000190, and so on. Each of those lengths has only 3 significant figures, so we would want to round this to 0.0000190. Remember, those first 4 zeros are not significant. Finally, a density. Let's use the 12,000 grams and 0.2670 liters. The mass has only 2 significant figures, so when we do the calculation, we get 44,943. We want to round that to 45,000. Let's practice adding and subtracting. I've got some addition, a subtraction, and an addition here. Your calculator answers are as follows. This one is where you really want to rewrite it and line up those decimal places, because then you can really clearly see that you'll want to round to the tenths place on this one, and on the second one you'll want to round to the hundredths place. So that would end up giving us, for the first one, 45.598, so that would round to 45.6, and for the second one it would give us 2.6959, which we would want to round to 2.70. Let's say I'm doing a unit conversion with a metric to imperial unit, 1 inch to 2.54 centimeters. If I have 35 centimeters, what is that in inches? Here I do need to consider my significant figures on the conversion factor. I actually have less in this case on the actual measurement, 35 centimeters. That's kind of the way it's supposed to work out. So that would round to 14 inches. But if I measure more carefully and I have 16.32 inches, I have 4 significant figures there, Then if I'm only using 2.54 centimeters to an inch as my conversion factor, then I need to round to 3 significant figures, or 41.5 centimeters. So I'd be better off looking up that 1 inch to the inch to centimeter conversion and retaining more decimal places on that, so I could have a slightly more accurate final calculated measurement.